Just look at this Excel-like editor. We developed these two co-authors are Frédéric Vautrin, Mathieu Barrault, Fabrice Rossi, and myself. Here you have this set, for example, here is time from 1960 to 2000, and here are, actually they are what is called in epidemiology ASR, that's standard average ratios for cancer death in different countries. Here you have Costa Rica, Mexico, and so on. And what are the columns? The columns, it's okay, they're very accessible. The columns are bins, age bins, 5 years age bins, because the evolution of cancer trends is not the same one for when you are from 75 to 79 years old as when you are from 40 to 45, 44 years old. As you can see here, you have a mapping of the situation, a global one, where you can see what happens. For example, we take, why not, UK. Is UK somewhere? And then UK here? Yes, United Kingdom. United Kingdom is very interesting because it's one of the few situations where this is lung cancer decreases along those years from 1960 to 2000 at a certain point. Here, Kingdom, you see from this point it decreases, and it's the same thing for all age groups, you can say. There's about the 70s, the cancer ratios for lung cancer, death, decreases. Whereas, if you look for Hungary, the situation is completely the contrary. It increases for all age beings on the same period. If you look at France, where is France? Here is France. France is rather flat, but slightly increasing, and then slightly decreasing in the last years, but very slightly decreasing. And we have other patterns as the United States is increasing until about the 90s, and then slightly decreasing also. So, you see here multidimensional set of time series. It's a complex set of data. As I tell you, time is complex. And when we want to look at time, not only in a very simple way, I mean just on a line, but we want to look at what time means for some problem as cancer death. You have, just for the data to explore a very complex situation, and you can't reduce it to just one vision. That's very important because you listen on the radio, on the newspapers, cancer is okay, cancer is decreasing, and it's not at all true. It depends on the age being, it depends on the countries, it depends then, of course, of social economic level of people. It depends on a lot of things. It's multidimensional. And you need multidimensional approach to treat those data. So this is only an editor. But this editor, you will see this afternoon, we will have some demonstration of the two, has been developed, and you have many tools to pre-process the, I hope I'll find something to, where is the pre-process? It's terrible because I lost these, this was the table we saw. It's, yes. too jealous, way too exercise. It's not only long. You have many, many, many ways of entering the problem, and you have to look and to explore what is going on. So an issue was to discover the most similar evolutions among countries. To think if there was a common pattern among countries in epidemiology for lung cancer evolution. And to find that, we had to provide a clustering of the data. To cluster the data, I used, I'm sorry because I don't know what happened, but everything is, I used, maybe I have something else, similarities because you want, between two curves. There are lots of indexes for that. Of course, you have to pre-process the data as, for example, if the time codes are not the same one, you use dynamic time warping. If you have two non-homogeneous functions, you have to smooth them and then to consider also the derivative, of course, because what is important for a time series, there are three things: level, variation, and changes, that's breakpoints. And you have to look for these three elements in a different way. And so you may have different tables to join in order to gather the richest information about the curve. And so it's a tough work to do, and you need to have special tools for that. So it's not only looking at the raw data table, but you have to transform it by different pre-processing moments. Well, imagine that you have the right curves to compare. So here you have, in the literature, different dissimilarities measure you can use. For myself, I've used a dissimilarity based on the Kuhl-Black-Leyer divergence because it was of some use for an application that I had to do. And it was, I thought, a good one. I normalized by L1 at first, and that was the right entry to my problem. So you have to define your dissimilarities, and then you have to merge the dissimilarity on the different variables. So you have to have an aggregation index, can I say, formula to deal with all the dissimilarities. And then you can run the clustering process with the clustering algorithm. And, yes, it's a time, that's okay. I had the result that I can share them to you. And then you obtain the clusters. But I did something more. Every day yesterday spoke about pyramids. I used at the very end of the process a pyramidization of the terminals, because Edwin said and explained that a usual clustering gives not at the bottom here of the leaves an easy interpretable order. You have to pyramidize the results. And so we did it. Our clustering algorithm is originally has different steps, and the last step is a pyramidization of the terminals in order to read directly the order of the elements. And we made a joint work with Catherine Pardoux, who is here in the room. And it really has been very useful because we had different products which were transported in France by railway, by road, by boats, and so on. And we had to classify the the variables which were able to explain, because we had a projection problem and a real prediction in sense of time prediction, not in sense of prediction of machine learning, just you have like a new pointer level. We had a prediction problem, that's a prévision. And so we had to choose, for this purpose of selection, a good feature a priori, because we had too much, and the models should have very few features in them. And so we did it with the parameterization, because here you look it appeared very simply which were the good time series next to the others to be used in the models. And so we highlighted our then explanatory model, whatever it was, regression and so on, with this feature selection based on the basis of the diagram. And to finish with, I just go back to the abstract. I'm sorry, as I'm not the original global. I use the abstract which you have on the website. So this is our website abstract. Okay. So this is the editor I talked to you, where you can then look very precisely to some curves. But the problem, very much more difficult problem that we have to face with Bernard now, and in some ways we face it, Jean-Marc did some work with me on that, is, as you said, Frédéric, to reconstruct sets of functions from sets of functions. But in a particular way, here it's in a structural framework. So we have a graph, and we have another graph, a reverse graph. Of course, from lung cancer to latent variable with sets of variables which are socio-economic, ecology, healthcare, nutrition, and so on. And we have a very huge database all over the world for this data. And from this data now, we want to reconstruct the ratio of death in lung cancer. Actually, we did already some work, but not in the functional framework, in structural framework, as we did it. We did it with lasso and algorithms just available on SAS, and we found a very simple thing like environment, smoking, were verified as explanatory variables. The first variable which makes the difference between countries is the socio-economic level of money. And that's the very first variable. So we wanted to go further and to do a better way and to use appropriate models, structural models for functional data analysis. And this is to do